I've been asked to talk about GFDL land modeling in 7 minutes. I think I just want to do you like a little sampler, like what you get in a restaurant when you go in the beginning, like a little appetizer dish. And next, John. Okay, and we have 4 versions of the land model, and we officially never had LM1 or LM1, but it exists, and in that sense, that's a giant on whose shoulders we're all standing, and that giant is Suki. So in some sense, Suki created not just climate modeling, but land modeling for climate purposes as well. And if you look at these 2 pictures, that's 2 illustrations from 2 papers which Suki published on climate and ocean circulation, part 1 and part 2 in Monthly Weather Review. And it's already set up the view, the philosophy that hydrological cycle is important and energy exchanges are important. Water, you need to worry about soil moisture, you need to worry about snow. That's why I think it was so natural that Chris moved to GFDL, I guess, and become our de facto the land modeler at the time. And I think it's also funny that in Suki's paper, land is actually more than the ocean. So I guess Suki had that premonition that land played an important role. Next, please. So, and the model which Chris built pretty much by himself with help of Chris Tadan and his postdoc, Andrei Shmakin, at that time, was called LM2, also was known as a LED, standing for the land dynamics. And that's the model which was integrated in the first GFDL flexible modeling system. It built upon what Suki had with a number of refinements. And it became component of the SIM2 model and all the other variants of SIM2 which were built after that, SIM 2.0, I think. So, and it has the same concept of hydrological cycle interaction, but Chris, being hydrologist, brought up awareness of other components, not just what on the surface. We had some representation of the groundwater, snowpack, but it also, Chris introduced this idea that vegetation could modify evapotranspiration coming from the land surface. And I also would say that Chris introduced the idea that heterogeneity is important, because before that, land pretty much had homogeneous characteristic in the original R30 model. So I'll just give you an example. There were parameters which were different by vegetation cover, and also parameters which were different by the soil properties. So a lot of work been done with SIM 2.0 after that, and LM2 was a very big part of it. After that, in about I'd say several years, up to a decade, we moved into LM3. John, can we go to the next one? So, and that's actually the first time LM3 sort of become a new flavor of the land model. It's become a model which represented not just energy balance and energy exchanges, but also biogeochemical interactions. That's what made it a component. We had land physics and hydrology, which Chris continued to improve, but also interactions with plant ecology and the land use, and heterogeneity due to land use. So GFDL LM3 was used in a SM2M and SM2G model, but also in the new model SIM3, which had interactive chemistry. And it also became a starting point for several Earth system developments at GFDL. Our postdoc, Minjin Lee, worked together with me and Chris, Sergey, and many others to introduce not just water quantity, like what Chris had already in the rivers and lakes and in soil, but also to introduce water quality through ability to trace nitrogen from the point when it hits the soil and through the river system and lakes into the water. So one thing which people don't appreciate that Chris did, and it enabled a very rapid development cycle, that our water had ability to have tracers in it. So even before we thought about any nitrogen or carbon in it or phosphorus, Chris sort of envisioned a way to sort of structure the model conceptually to have actually that ability to add the tracers. That's why I think we succeeded very fast and built the first model, which had a water quality in the riverine system and delivery of nitrogen to the ocean. Because at the time we went from the bucket water to the soil layered water, we were able to distinguish soil water profiles in the surface from deeper layers and all the way down to the bottom. And because we knew exactly how much soil moisture model could simulate at the surface, you could start to think about other interactive cycle like dust. So, you know, for the processes of dust simulation, soil moisture, one of the key inputs. So Stuart Evans, who was again our postdoc, and like collaborated with us and built a model which was able to know it, not just where the dry places are, but how much dust emissions are coming from them. In parallel, a Princeton graduate student, Sam Rabin, and later on another postdoc, took again information about soil moisture and made it like a precursor of the wildfire model. And later on, a couple of collaborators from atmospheric chemistry, Fabian Poulot and Myung Lin, were able to link the position of nitrogen and ozone to the state of the land, including how much vegetation there and what the soil moisture and so on. And all of those developments were enabled essentially by this vision which Chris had. So you need to know not just how much water it is, but where it is. And also you need to know what's happening with the water and related traces in the river system. You know, because in previous models, water was magically teleported to the ocean. Now we could actually track all of those streams. And because we had river network, we could look at the analysis of stream flows and possible floods impact. That Sarah and her postdoc led a paper about that. Next, please. John, click one more time. Thanks. So you see a picture on the left. That's actually a picture which Chris developed himself. And it sort of shows that Chris has his aesthetics about how he does. His work is always very elegant mathematically. You know, implementation and approximations are really, I think, you know, done with not just being good mathematically, but the way he thinks about framing them. And it translates all the way down on his writing, like I think Sarah acknowledged, but also in the way he illustrates things. And I think, you know, I really like this picture and, you know, how we have all these essential processes of fire and water. But it also, I think, reminds me that there's certain aesthetics for overall research and communication, which Chris always had, and he encouraged us to write well and present our research in a good way. So on the right, you see the laundry list of all things we are doing now in LM4 model, and I'm not going to go for them. It's all sorts of things. It's much more than Sukieva probably wanted. It's something that I think a lot of people are interested in, stakeholders. So, and we're able to expand what was in LM3 into LM4. LM4 no longer is just one model. It's actually several models which are configured from the same system. So LM 4.0 is used in CM 4.0 in a sphere, which is our prediction model, which Tom spoke about. LM 4.1 is a component of ESM 4.1, and we have all sorts of things we do in an LM 4.2. And you see some stuff in red there. It's still developments which have paper written about, we have analysis, but they're not all been sort of brought together under the same umbrella. That's part of the work we're doing now. Can you please go next? And this is just sort of, again, a little dessert on our sampler to show what are we actually doing now. And one of the concepts we start working together with Chris, I would say like more than a decade ago, this idea that we need to go away from the flatland and think about effects of orography and geomorphology and hill slopes, where water goes not just down, but how does water actually flows in 3 dimensions on the land. And Chris pioneered this idea, which I don't think he gets credit for that, how to get that complex orography represented in terms of hydrological processes. So we came up with the idea, and Chris essentially kind of enabled that work, is to break each grid into tiles. You can see that in the middle, in that little, imagine that you have an atmosphere on top, which is invasion, and then you have the little sort of a carpet of different colors. Those are actually different hill slope and elevation tiles, and they can connect it. And we could use high resolution data. That's a work which Ned Cheney did, and he's going to speak more about it. And then we could basically channel the water between those tiles, and each of those tiles communicates separately with atmosphere. Later on, we added not just hill slopes, but elevation slopes, and we know now what the aspects are. So current postdocs like Enrico Zergetto work on the effect of the aspect like south-facing slope and north-facing slope. How does it affect on the heterogeneity on the land, which is a much smaller scale that atmosphere is able to resolve right now. And also we exploring in this approach how to compute not just the water in the soil, but how much water on top of the soil. That is a little thingy there on the right. We extending these approaches to representing inundation now, so we can make dynamic wetlands. And the reason we need to do all of that, because ultimately we need to go beyond methane, beyond carbon, and look at other things like methane, which requires knowledge where wetlands would be. We also need to know where the effects of reservoirs, and Chris did a lot of work with Eugene, and Eugene's going to speak later about on irrigation. And the new things we're doing now, also exploring how to run this model in initialized mode on land from, initializing soil moisture and vegetation structures, so we don't have to spin out model to death when we need to do predictions. So in that sense, I think what Chris earlier work on LM2 and LM3 did, it sort of guided our processes, understanding and thinking about how to get land, which is much more complex and heterogeneous than some of the atmospheric structures, but do it still in a computationally feasible way, and in a way that you could communicate back to stakeholder on the scale which they need, what is actually soil moisture at the scales of 1 kilometer or 2 kilometers without actually simulating every kilometer under the sky. So I think without Chris, we probably would not be in the place where we are. And I think, we still hope that Chris would be interested in what's happening with the seeds of hydrological modeling he gets into work which our current postdocs are developing. So I'm just pleading to Chris, stay in touch, and hopefully you could still find the work postdocs are doing are interesting, and hopefully they're not making anything crazy and break the aesthetics which you built. Thank you.
Lena, as usual, you're challenging me to do more, and that's something I really appreciate about the time we spent together. We're very different as far as our temperaments and our vision or detail and all that stuff, but we had a little rough time, I think, at the beginning, but we really hit our stride, managed to get together really well, and had a great complementarity as far as the two things being much stronger than either one. And I'm, just happy to be, able to hand the baton over as far as model development. I mean, that's happened 10 years ago. I mean, it happens over time. But yeah, it's sometimes I'm going to say this in my talk, but I'll just mention, you often challenged me to go beyond my comfort zone, and sometimes you were pushing too hard, and sometimes you were right on the mark. You always forced me to think, what makes sense to me, what am I capable of, and I really appreciate that. I wouldn't have done as much as I had if it weren't for you. Thank you.
Thanks, Chris. I read in some book on the self-help when I was younger that, if people have relationship, if you call them and they pick up the phone. So I think that's kind of relationship we have. If I send Chris an email, he responds. And I think it's also a sign of, Chris's engagement and commitment. Because, I think Chris retired, but I don't believe he left us. So in that sense, I very happy that I had an opportunity to get to know you, work through our differences. And I think it's also signs of, commitment to science. You want to find out what's the best for the model, for the lab, not necessarily for your personal comfort zone. So in that sense, like, I'm really happy, and I consider you one of my mentors and friends. Thank you.
Thank you.